Hello 8th graders, today we're starting in on the next unit, which is all about Newton's third law. This is going to be a pretty short unit because we've already introduced the topic, but what we have to do is we have to talk about Newton's third law in terms of momentum. So the very first part or lesson in this unit is called Conservation of Momentum Concept. The next time that we talk is going to be part 2, and we're going to get into conservation of momentum with the equations. So today is just understanding the concept. So I need you to be in your notebook with the notes and a practice side. Find a nice clean page for both if you don't already have those, and make sure that you're making a header and a title so that you can find this again when you need it for the assessment. Before we get into the lesson, I need you to go over to the practice side and complete the warm-up. So the warm-up for today is, suppose you were going to be competing in a home run derby, and of course you want to win. So you want to give yourself an advantage to be able to hit more home runs than the people that you're playing against. But here's the trick to this. In this home run derby, you are allowed to modify the bat and the ball in whatever way you want, except that whatever you do, it has to be powered by you. So you can't be like, I'm going to add springs to my arms and rockets to the ball and all of that. No. It has to be powered by just your arm power. So what would you do to give yourself an advantage and why? Think about the materials. Would you choose heavy materials or light ones? And explain why you would do that. Your hint is that today is all about momentum. You want to give that ball momentum in order to win the home run derby. So how would you do it? Pause the video and answer that on your practice side now. If you're still watching, you've answered the warm-up question. We're going to come back to your answers in just a second. First, let's talk about the objectives. These are actually the 2 objectives for the next 2 lessons. We're going to do number 1 today. Your job today is to explain the law of conservation of momentum, which is actually another way of saying Newton's third law. So we've talked about Newton's third law already. We just have to do it today with momentum. The next time we talk, it'll be about calculating using the law of momentum. So let's go back to your warm-up. If momentum is mass times velocity, we want to give that ball a whole bunch of momentum. And the thing that you probably already intuitively understood, which means like you already kind of knew it without knowing that you knew it, was that momentum can be transferred. So if you want to make a ball go really fast, you have to put momentum into it. And that momentum has to come from somewhere. And in this case, the momentum comes from the bat. So if you want the ball to get a whole bunch of momentum, that means the bat had to have a whole lot of momentum so that it could transfer. All right, so let's think about that bat. If momentum is mass times velocity, we want the bat to be heavy, and we want the bat to go fast. The trick in baseball is I want that thing to be so heavy that it's got a lot of momentum, but not too heavy that I can't even swing it. So if you have a heavy bat and you can swing it fast, maybe you want to work out first, then you're going to get a lot of momentum to transfer into that ball. Now thinking about the ball and its momentum. We don't really want the ball to transfer momentum again when it like hits somebody's glove or gets far out and hits a wall or something. Instead, we really want that velocity part. We want the ball to go fast. So if you want a really fast ball and you're putting some momentum into it, if the ball is heavy, that's kind of like soaking up some of that momentum. A heavy ball going really slow can be a lot of momentum. But if you take that same amount of momentum into a light ball, that means it's going to go really, really fast. So a heavy bat and a light ball might be the perfect combination. In order to investigate this a little bit further, we're going to go and do a Newton's Cradle simulation. If you've never seen those, it's one of those like marble things that sits on people's desks sometimes and clicks back and forth. We're going to use a digital one of those, and we're going to make some conclusions about how it works. Here's what it looks like. In Google Classroom, it's called Newton's Cradle Investigation, and your mission is what's in red up at the top. Your mission is to write a statement. So that could be like a sentence, maybe 2. And that statement needs to serve as a rule for how these Newton cradles work. It's going to sound something like every time you do this with a Newton's cradle, you always get that. It's a rule that defines it. So no matter how many marbles you start with or how high they're starting with or how many on each side, doesn't matter. The rule needs to state what is going to go in, what does that mean is going to come out. In order to get to the simulation, there's another link in Google Classroom. It's also here on the document, but the actual interactive looks like this. You can choose from all these settings for how many you want to start with, but you can also just drag them and move them around on the screen. We reset. You can drag them and move them around like this, and you can set it up however you want. In the document, here's what you're going to be working on. The first thing is this data table. It tells you how you're going to set up the simulation in the white boxes, and you're going to put in what happens in the blue boxes. So it tells you how many bearings, those are marbles, how many marbles or bearings that you're going to use, and how high you're going to set them up. In the blue boxes, the first one is how many popped out on the other side, and how high did they go. The way we're going to measure the height is we're just going to call it normal, high, and low, because we don't have a ruler or anything. So if you reset the simulation, whatever it starts it at, this looks like at about a 45-degree angle, we're going to call that normal. If something pops out on the other side like that, that would be lower than normal. If it pops out the same amount, we'll call that normal. And if it pops out higher, we'll call that higher. That's how we'll measure these three things. After you've recorded your data, then you need to go to the 5 analysis questions at the bottom. The first 4 lead you into the last one, and the last one is definitely the most important. This is where you're going to answer that big question. What is the rule for how a Newton's cradle works? I left you a sentence starter that looks like this. It says, starting with blank, blank is the result. And of course, you could fill in the blanks. If you have another way of saying it, you don't have to use my sentence starter. But the goal is to say, what is the rule for a Newton's cradle? Every time you do this, what's the result? Pause this video and start on the Newton's cradle now. If you're still watching, you've completed the Newton's cradle and you've written a rule for how it works. Let's talk about if we agree on the same rule. So in a Newton's cradle, it's clicking back and forth. Eventually that Newton's cradle is going to stop due to friction, but using the virtual one, we get to ignore friction and just think about what's happening in terms of Newton's laws. Since this is all about momentum, this is basically a little momentum machine, let's go back to the equation for just a second. Momentum is mass times velocity. The way we talk about mass with a Newton's cradle is just talking about all the marbles. Since each one has the same mass, we can say like 1 marble got dropped and 1 marble came out on the other side in order to talk about how the mass might have changed. For velocity, that's what height is all about. If we drop it from normal height and a marble pops out on the other side, also at normal height, we could say that the velocity stayed the same. So the rules for this, if you don't have something similar to mine, you're going to change it or add to it. The momentum that goes in on one side is always the same as the momentum that comes out on the other side. In real life, we would subtract friction, but in this situation, we get to ignore it. So if you drop 1 marble from normal height, you're going to get 1 marble from normal height on the other side. Whatever momentum went in was the same that came out. If you drop 2 from really high, you're going to get 2 on the other side. Let's check to see if this works for some stranger situations. So let's test this one out. Let's say I'm going to drop 1 marble from normal height on both sides. So think about the momentum that's going in. We have some momentum going to the left and some momentum going to the right. And if our rule is right, what should happen is we should get the same things coming out. We should get 1 amount going left and 1 amount going right. And that's what happens. They bounce, and we get the same amount coming out after every collision. Let's test this situation. What if we have 2 marbles going in from the left side and 1 marble coming in from the right side? If our rules are correct, whatever goes in must come out. We should have 2 coming out on the right and 1 coming out on the left. And so it should kind of switch sides each time there's a collision. Let's check. And that's what we get. The 2 switches sides because we get the same thing coming out that went in. So check your work. If you don't have something similar to the rule that I have on my screen, I need you to go back and change it. If it's not the exact same as mine, that's totally fine. The key word here is something about being the same. Whatever goes in on one side has to be the same as what comes out. If you wrote it another way in different words, but said the same idea, then you've got the right answer. Before we get into the notes for this topic, let's quickly remind ourselves of what we did in the last unit. So Newton's third law is that for every action, there's an equal and opposite reaction. So we talked about how if you push on a wall with 100 newtons of force, the reason why you don't fall over is because that wall is pushing right back. with 100 newtons of force, equal and opposite. That means that actions are always balanced. If ever there's a force, if you're pulling on a rope in this direction, that means there has to be another force in the same amount going in the other direction. They're always balanced. There's always something canceling it out from the other side, is what Newton's third law is all about. Well, we're talking about momentum today. So let's say that I want to give this object some momentum. A momentum that's going into this ball has to come from a force. In order to give something momentum, you have to push on it. So since momentums and forces are related to each other, the rules work the same way too. So I have on my screen, momentum is a measure of how hard it is to stop something, and it requires a force in order to give something momentum. That means that momentums are balanced too. So for every momentum going that way, there has to be a momentum going in the opposite direction all the time, according to Newton's third law. Let's think about a golf ball and a golf club in order to help us get our head around this idea. So if you imagine a golf club swinging in and it's about to hit a golf ball, that golf club, when it hits the golf ball, it's going to slow down just a tiny little bit. And that's because the ball is pushing back on the club while the club is pushing on the ball. Well, if the club gets pushed on, that means it's going to slow down just a tiny little bit. Well, the ball, on the other hand, is going to go speeding up because the golf club pushed on it. There were equal and opposite forces. But here's the thing. The energy that the golf club lost, the momentum that it lost by slowing down just a little bit, it went into the golf ball. None of that momentum was lost. All the momentum we started with happened to just be in the golf club. All the momentum that we ended with, some in the golf club, some in the golf ball, that amount is the same as what we started with. And that's what Newton's third law is all about. You can't destroy the momentum. It has to go somewhere. Let's get this into your notes. Over on the note side in your notebook, I need you to make your page look like my screen. First thing is we're going to write Newton's third law, but using the words momentum this time. So all of the momentum before a collision must be equal to all of the momentum after a collision. That's where we're going to start. Let's use some examples too. So you can use like little stick people in order to put this example in your notes, but you do need these two examples. Let's say that we've got this kid who's just standing on a big sheet of ice. The reason why I have him on a sheet of ice is so that we can pretend to ignore friction. So pretend there's no friction. And we toss him this little ball. The little ball has a tiny amount of momentum. So if you imagine this whole setup, the boy, the ball, and that's it. That's all we're paying attention to. The boy has zero momentum because he's just standing there. The ball has a little tiny bit of momentum. When the boy catches the ball, all that momentum has to go somewhere, and it's going to go into the boy. And so he's going to start sliding back because he got the momentum transferred into him, and that's going to come out in the form of him moving. If something with a little bit of momentum crashes into you, your momentum will go up a little. But the point is that all the momentum is equal. Before the crash, it was just all in the ball. After he caught it, that's the crash. Now it's in the boy and the ball, and they go sliding. That's where all the momentum is after that. Well, what if we instead shoot him with a cannon? There's a huge amount of momentum coming out of the cannon because the cannonball is really heavy and it's going really fast. So a lot of momentum. The boy, again, is just standing still, standing on some ice, so he has no momentum. If instead of just getting obliterated, let's just imagine for a second that he could actually catch this thing. Well, that means that he's going to go sliding back a lot. He's going to take all the momentum with him. If something with a lot of momentum crashes into you, your momentum goes a lot. But the point is that it's still going to be equal. None of the momentum was lost. It would just transfer into the other object. Pause this video if you need to add any of these parts to your notes. Over on the right side, I need you to do stop and jot number 1. So this is going underneath your warm-up. If you were worried about getting hurt in a car accident, would it be safer to drive a big heavy car or a small light one? And I need you to explain why by talking about momentum. And I'm going to give you a little bit of a hint. In a car crash, the thing that hurts you is a giant change in velocity. So if you're driving really fast and you crash into something, all of a sudden your body has to slow down really fast. That's the part that hurts you. Think about it the other way. Let's say you're sitting at a red light and somebody smacks into the back of your car, and all of a sudden you go flying forward. You speed up really quickly. That's the thing that hurts you. So changes in velocity is what causes injury in a car crash. So does riding in a big car during a car crash help with that? Or does riding in a small car help with that? Or does it even matter? Answer over on your stop and jot side. Ready, go. So if you're going to put momentum into an object, and that's what's going to happen during a car crash, your car is going to get some momentum put into it. Think about transferring some momentum into a huge object, like this big car on the left. If you put momentum into a big object, it's not going to speed up very much. Think about kicking a car. If you kick a car as hard as you can, which would be a really dumb thing to do, but let's pretend. You kick a car as hard as you can, that car might shake a little bit. It's going to move just a tiny bit. That momentum from your foot didn't change the velocity of the car very much. If instead you put that same kick into a soccer ball, a really small mass, that soccer ball is going to go flying because it has such a small mass. But the same amount of momentum from your foot went into both things. The result was so different because of the mass of the two things. So transferring some momentum into a small mass is going to make it speed up more. That means that the bigger car is going to be safer in a car crash. Back over on your notes side, let's talk about another way to think about Newton's third law, and that's explosions. An explosion is a collision in reverse. Imagine that you had a slow motion video of a grenade blowing up. You could imagine all of those parts and pieces all flying out in all sorts of different directions. Pretend like you could watch that thing in reverse. You would watch all the little pieces come flying back together and form a grenade again. That's all the pieces coming together. That's what a collision is. So an explosion is just all the pieces flying apart. A collision is all the pieces flying together. Since they're just the same thing in opposite directions, the rules work the same. So on your note side, I need you to have what's in red. All of the momentum before an explosion must be equal to all of the momentum after an explosion. And in physics, an explosion is just more than two objects, or two or more objects, flying apart from each other. So in the video that you see on your screen, this is technically in physics an explosion. The two girls are sitting on carts and they push each other apart. They each push on each other with the same amount of force. So the force is the same because of Newton's third law, but also because of Newton's third law, the momentums have to be the same too. And they're balanced. So think about the two girls sitting there right at the beginning. They're not moving, so their momentum was zero. They push on each other and they both go flying apart. They have about the same mass as each other, so they both go flying apart at about the same speed because they have the same mass, same momentum. Everything's the same. However, if you were to add up the momentum of the girl in the blue shirt and the girl in the white shirt, one would be positive and one would be negative. Call them each 10, let's say. A positive 10 and a negative 10, that still adds up to zero. So before the crash or the explosion, they were zero. After the explosion, add them together, still zero. Over on your practice side, I want you to make a prediction. In this situation, they've added the teacher onto one of the carts, on the one on the right. I want you to predict, what should happen when they push apart now? When they push apart, what's going to happen? Please record it on your practice side. You should be using the words momentum, mass, velocity in your answer. Come back when you're ready. So in this situation, when they push apart, the girl on the left, she still has the same momentum because her mass didn't change. Her velocity didn't change. Everything for the girl on the left is the exact same momentum. But the people on the right, because now we've increased the mass so much, the mass is huge, that means in order to have the same momentum, the velocity had to shrink down to be really tiny. So they still move a little bit, it's just a really small amount. However, if you were to still add up the momentums, before they pushed apart, they were just sitting there, momentum was zero. After they pushed apart, one was positive, one was negative, but they were the same amounts, and so they would be canceling each other out. Now we're going to do a quick demo. So I have a few sporting goods here with me in the room. I've got a softball, tennis ball, golf ball, and ping pong ball. What I'm going to do is I'm going to drop them together like this with the tennis ball sitting on top. They're going to get dropped together, and when they hit a surface, what happens when you hit something really hard like concrete, like what I have in this room, Think of concrete as like a momentum mirror. It just reflects it right back. So if you drop things by themselves, that's why they bounce, because the momentum hits the floor and just gets pointed right back and it bounces off the floor. However, if you do them in pairs like this, something interesting happens. The momentum from the bottom object can get transferred into the top. So they're going to bounce together, or they're going to fall together, they're going to hit the ground, and the top object gets like a shot of extra momentum. So that we can compare these things, let's take a look and see how these objects bounce on their own without any added momentum. Now we're going to take the tennis ball and we're going to put it on top, and that momentum from the softball is going to get transferred into the tennis ball. Let's see how that looks. As you saw, the tennis ball got a shot of extra momentum and it went flying up into the air much more than it did when it just bounced by itself. And that's because the momentum from the softball was transferred. And if you go back and listen to it, when the softball bounces, you can hear it hitting the ground a few times. When the softball bounces with the tennis ball on top, listen closely, you hear it just hit the ground just one time, and that's because all the momentum was put into the tennis ball. So here's what you need to do. Over on your practice side, please make a little header that says demo so I can find your answers, and I need you to make some predictions. Number 1, what will happen when I do this arrangement with a golf ball on top? The golf ball is much lighter. And why? And then the next one, what's going to happen with the ping pong ball sitting on top? And of course, why? And then what would happen with any of these objects if I did it from like twice as high, or maybe from the top of a building? How would that change anything? And of course, why? Pause the video and answer those on your practice side now. Now that you've answered them, let's see if you were right. We're going to start with the golf ball and then with the ping pong ball. Let's see what happens. As you saw, the golf ball went flying much higher than the tennis ball did, and much higher than it could by itself, because that momentum from a big heavy object put into a small thing means a lot of velocity. Then when I took the ping pong ball and I put it on top, that same amount of momentum was transferred into an even lighter object, and it went flying so high it went off the chart and even hit my ceiling. It got so much velocity because it couldn't handle all that momentum. It's so light. Before we wrap up with the closure, I need you to do the concept check, which is a Google form in Google Classroom, and complete the 4 questions before moving on. For your closure, since we started this whole unit, or this whole quarter actually, by talking about hand judo, I need you to think about hand judo in your closure answers. So when I face off against my son in hand judo, who experiences more force? When we push against each other, who experiences more force, me or my son? Question 2, which person will move with more momentum? So when we push off each other, who gets more momentum? And then question 3, which person will move with more velocity? And the all-important why. You must explain your answers in all 3 of these. Why do you say what you say? Pause the video and answer these on your practice side. Make it nice and clear. Write down closure so I can find your answers. If you're still watching, you've answered the closure questions. Let's check in. Newton's third law says that all the forces have to be equal. I know it doesn't seem like it, but in order for me to push on my son, I have to receive a force back in the same amount in the opposite direction. So if I push with 100 newtons, I'm also receiving a force of 100 newtons. They're equal. And because momentum and forces are related, Newton's third law says that the momentums are equal too. If I push on him and give him some amount of momentum, I also receive the same amount of momentum in the opposite direction. The thing that's different is our velocities. If my son gets a certain amount of momentum, because his mass is so little, that means that his velocity's got to make up for it, and he's going to go flying quickly. For me, if I get the same amount of momentum, my mass is so big that my velocity is going to be tiny, but we both receive the same amount of momentum. And this is why I have a huge advantage in hand judo, is because if I get a little bit of velocity added to me in the form of momentum being added to me, it's really easy to recover from just a tiny bit of velocity. But for my son, who has a lot less mass, all that velocity added to him is going to be really hard to recover from. That's why I usually win, since I'm bigger.